problems.
Assalamualaikum and hello everyone, I am Husna and this is my friend Nabila.
Hi, hello everyone. Hope you guys having a good day.
So in this video, we're going to talk about things related to quantum physics.
Do you guys know what is quantum physics?
It sounds so strange, right?
Basically, the idea is the particle, or at least the behavior of the particle, is described by wave. But if you guys want to know more about this quantum physics, so let's check it out together.
So, quantum physics is the part of physics that describes the smallest thing in our universe. Molecules, atoms, subatomic particles, things like that. If you've heard of something called a proton, a neutron, an electron, a photon, those are examples of quantum particles. Things down there don't quite work the same way that we are used to up here. This is fascinating because you and everything around you made from quantum physics. And so this is really how the whole universe is actually working. These protons, neutrons, and electrons have been drawn as particles, but in quantum physics, we really describe everything as waves. So instead of electron looking like this, it should look something like this. This is called a wave function. But this wave function is not a real physical wave like wave on water or a sound wave. A quantum wave is an abstract mathematical description. To get the real-world properties like position or momentum of an electron, we have to do mathematical operations on this wave function. So, with quantum physics, we don't know anything with infinite detail. We can only predict probabilities that things will happen. Another confusing thing is how exactly to picture an electron. It seems to be a wave until you measure it, and then it is a particle. So, what actually is it? This is known as particle-wave duality, and here is an example of it in action, the famous double slate experiment. The idea is that it is the electron wave that goes through both slates at the same time, and then the waves from each slate overlap with each other, and where the waves add together, you have a high probability of the electron popping up at the wall, but where the waves cancel out, the probability is very low. So this shows that electrons behave like waves in this experiment. Now, for entanglement, let's say two electron waves meet. Their waves interfere with each other and become mixed up. This means that mathematically we now have one wave function that describes everything about both electrons, and they are linked, even if they move far away from each other. So, where does the name quantum come from? Well, a quanta is a packet of something, like a chunk or something. And one of the first quantum effects people saw were atomic spectra, which is where atoms give off light with the specific discrete energies. So, to round up, in quantum physics, objects are described with wave functions, but when we measure them, what we see are particles. So, this leads to particle-wave duality and also the measurement problem. Let's go back to the 1890s. The first problem came in the form of nature of light. Is light a wave or is it a particle? Well, experiments show it is both, but scientists were unable to explain its true character. They wanted to know what is light, and this was a topic of debate since the 17th century. The second problem was the Blackberry Spectrum. In 1900, a group of manufacturers approached Max Planck. For those who don't know about Max Planck, he is the father of quantum physics. The manufacturers wanted to know the method of making their bulbs efficient. This required a better understanding of the Blackberry spectrum. Max Planck came up with the solution. He said that energy emitted from a radiating source is quantized. Radiant energy is made up of particle-like components known as quanta. So Planck replaced the concept of continuous energy with discrete packets. In 1918, Planck was awarded the Nobel Prize in Physics for his work of Blackbody radiation. Then came Albert Einstein. While Planck did not realize how radical this work was, Einstein sensed that something deep is hidden in this hypothesis. In 1905, he took Planck's idea forward and said that light is itself made of these discrete energy packets called quanta of energy. Other scientists, which are Albert Einstein, Niels Bohr, Louis de Broglie, Erwin Schrödinger, and Paul M. Dirac, advanced Planck's theory and made possible the development of quantum physics, a mathematical application of the quantum theory that maintains that energy is both matter and a wave, depending on certain variables. Quantum physics thus takes a probabilistic view of nature, sharply contrasting with classical physics, in which all precise properties of objects are in principle and calculable. Today, the combination of quantum physics with Einstein's theory of relativity is the basis of modern physics.
Introduction of Schrödinger. Schrödinger equation, the fundamental equation of the science of submicroscopic phenomena known as quantum mechanics. The equation, developed by the Austrian physicist Erwin Schrödinger in 1926, has the same central importance to quantum mechanics as Newton's law of motion have for the large-scale phenomena of classical mechanics. Essentially, a wave equation, the Schrödinger equation describes the form of the probability wave that governs the motion of small particles, and it specifies how these waves are altered by external influences. Schrödinger established the correctness of the equation by applying it to the hydrogen atom, predicting many of its properties with remarkable accuracy. The equation is used extensively in atomic, nuclear, and solid-state physics. History of Schrödinger Heisenberg metric mechanics. In 1924, de Broglie suggests particles are waves. In the middle 1925, Werner Heisenberg introduced metric mechanics. In late 1925, Erwin Schrödinger proposed wave mechanics. Both formulations are used today, but Schrödinger is easier to understand. The free Schrödinger equation. In 1925, Erwin Schrödinger proposed wave mechanics. Starting point, energy or momentum relationship multiplied by the wave function on the right. Use de Broglie relations to rewrite. Use relationship for complete wave to rewrite with derivative. Hamiltonian, what is it? In quantum mechanics, the Hamiltonian of a system is an operator corresponding to the total energy of that system, including both kinetic energy and potential energy. Due to its close relation to the energy spectrum and time evolution of a system, it is of fundamental importance in most formulations of quantum theory.
Probability interpretation tells us that its amplitude squared gives the probability for finding the particle between certain location. To find the probability that a particle is located within a given region, we have to integrate the wave function. This picture shows a typical wave function. The particle would be relatively likely to be found near A and unlikely to be found near B. The shaded area represents the probability of finding the particle in the range dx. Next, probability must equal to 1. Because of the statistical interpretation, probability plays a central role in quantum physics. The probability that x lies between a finite interval is given by the integral of probability density function.
Time-independent Schrödinger equation. Time-independent problem. Often the potential does not depend on the time, V equal to Vx. To solve this equation, we try a separation of variable. And then we plug this guess in. Divide by the original wave function. Note that left side is independent of x and right side is independent of t. Both sides must be independent of both x and t. Both sides must be equal to a constant called E, the energy. And we multiply by xy again. This equation is much easier to solve than the original equation. ODEs are easier than PDEs. It can pretty easily be solved by numerically if necessary. Note that it is a real equation, we do not need complex number.